It's no problem. Yeah, I'm glad that some of you come. Thanks for the invitation. So I will talk about quantum computing today. I'm Hiu-Yung. I'm a professor in electrical engineering. My office is just over there. So he said that I should spend 2 hours or 1 hour. It depends on you who need to live within 1 hour. Yeah, let's just make it short. Don't spend 2 hours on this boring thing. So I will first introduce myself and my lab and what is quantum computing and how it's related to electrical engineering. Right. Then we'll give some overview on the basics of quantum computing, error correction, and then their hardware. San Jose State U. These are the slides I usually show to the companies when I go out. And first I show them in my lab, we do TCAD simulation. This is a semiconductor simulation, lot of interest to you. And we also can do chip design and do cryogenic measurement. That student is doing a measurement on transistor at 4 Kelvin, liquid helium. You know what's the boiling temperature of liquid helium? I just say 4 Kelvin. So it's very low. Our room temperature is 300 Kelvin. And in order to cool to 4 Kelvin, you need a lot of energy. This one you know that, but I always show to the industry partner. We told them that our electrical engineering is pretty big. We have like about 800, 700 students. At the peak time, it was like maybe more than 1,000, right? But now it's coming back. But the point is that many of our students are the main employee in the Silicon Valley companies, Cisco, Apple, and many of us do the test engineer, product engineer, sales, application engineer, marketing, in addition to the design, tape out, verification, and you see Apple, Cisco, their number one employees came from San Jose State University, right? And that's why I told them you really should consider our students. Although we only have master students, we don't have PhD students, but they are hardworking. To be frank, the return on investment is much higher by hiring our students. Right. So in EE, we have 3 classes related to quantum computing. The first one, Introduction to Quantum Computing, is ordered before, is more about algorithm. The second class is cryogenic narrow electronics, where we study the low temperature. Cryogenic means low temperature electronics. For quantum computer, you need to cool it to very low temperature in order to make it work. So that's why you want to have low temperature electronics to make it close to the quantum computer and to reduce the to increase the throughput, reduce the latency, right? And E274 is quantum computing architecture. You talk about the hardware of quantum computers, right? So in 2006, next spring, I will offer 226, which is the cryogenic narrow electronics. You learn about the transistors and also circuits at low temperatures. We also have a program on quantum technology on Master of Science on Quantum Technology. Is co-housed under physics and electrical engineering. And then I have 2 books on quantum computer, programming and architecture. And you can look at my YouTube channel where you can get information about the quantum computing if you don't take those classes. Okay. Any questions over there about quantum computer? Anyone has question? Okay, so why electrical engineer plays a role in quantum computer? And actually, this is a niche market. You know, if you look at semiconductor, this is a complicated equation. You talk about the electron mobility. If you're taken E128, you learn about have you learned about electron mobility? Yeah, it tells you how fast the electron will travel under a given electric field. But in order to find the electron mobility, in E128, we just tell you what the mobility is, how it depends on the electric field, how it depends on the doping concentration. But in reality, you need to go through this multi-physics problem to solve the so-called subband, how they get scattered, and it's fully quantum mechanics. So there's a physics. But when it comes to electrical engineering, it becomes a very simplified analytical equation. And this is implemented in many software, including Synopsys and TCAD and Silvaco TCAD tool. It's a very simple equation, and they have a market volume of more than 100 million per year. They sell this software to different companies, TSMC, Samsung, IBM, and even NVIDIA, Apple. I know they're their customer because they're interested in exploring new novel devices, right? So as an electrical engineer, maybe we don't need to go through this Fermi golden rule or this complicated multi-body physics, quantum mechanics, right? But if we understand some of the basics, we can do very well, and they are priceless, means that they don't earn money, right? But for us, we do earn a lot of money. And same for quantum computer. This is a complicated equation and called the James Cummings Hamiltonian. Again, it discusses how a qubit will interact with the external environment, right? But for us, can you guys come up with something, a simplified equation? Because this is only to describe one qubit, but if you want to have a useful quantum computer, you need maybe more than 1 million qubits. And how do you design 1 million qubit by using this sophisticated equation? It's impossible. You need to come up with something that is simple, right? And that's why I want to say that, yeah, they are difficult, but we don't need to spend too much time on it, right? The poor physicists, they spend their whole life coming up with this equation. They do get Nobel Prize, but however, if we do it well, we get a very nice career, and the whole Silicon Valley is built up on electrical engineers, right? So that's what I want to say. How is it related to us? So here I show a quantum computer schematic. If you look at it carefully, only two parts are quantum mechanics. Here I have something called qubit, quantum bit, a transmon on a chip. Another called quantum limiter amplifier. You cannot explain this by classical physics, right? Everything is quantum mechanics. But however, in order to make this to work, you see that you actually doing everything you are doing in electrical engineering. On the top is a high-performance server. Inside this high-performance server, you have ASIC, FPGA, high-speed digital electronics, analog to digital converter, digital to analog converter. And then you go through this. Who know what this is? If you have taken any microwave class. This is called mixer. This is local oscillator. Local oscillator times mixer with the signal you generate a push to like 5 gigahertz, 10 gigahertz, and go through this attenuator. And they will reach, and circulator, they will reach your quantum chip. Everything is classical electronics. These are all the classes you have learned, from Python programming to FPGA, right? The class offered by Professor Shika, and all the way to here, the classical, right? And even this chip is classical. It's nothing is similar to the silicon layout. It's a resonator. It's nothing but just a niobium wire. And if you take the E140, I know they changed the syllabus a little bit, but all you learn in E140 are all about this. What are the quarter wavelength resonator that you might learn at the end of the class? Scattering matrix, right? Of course, before that, you need to learn the EM theory, Maxwell's equation. How this signal will propagate to here, interact with the qubit, and then reflect back. And then you go through the circulator, isolator, and then amplifier. So if you take like the graduate class E223, E230, right? You need to design this amplifier, amplify the signal, right? So everything is your domain, not the physicist. Okay? And how about algorithm? Right? So, and these are at low temperature. So I just want to tell you that 90% of a quantum computer belongs to E students. And the good thing is this. If you study this, and then the quantum computing industry doesn't work, you still can go back to EE because you still can do your 5G, 6G, 7G with the knowledge you have learned, right? And you can still be a data scientist with the programming knowledge you have learned. all these things, right? So let's take a look what is a quantum computer. So we do use quantum phenomenon in many things already, right? Like this display, your LCD, the transistor, your iPhone, everything is quantum mechanics. Because if you don't have quantum mechanics, you don't have solid state physics. You don't have Venn diagram. Then you don't have, if you have taken E122, you don't have diode, you don't have MOSFET. So nothing will work in this room if there's no quantum mechanics. But when we say we do quantum computing, what we are saying is that we do something called quantum 2.0. We use two important phenomena in quantum computer, superposition and entanglement, right? Directly to do the computation. Our transistor also has entanglement, has true superposition, but we don't use those properties for computation. What we do in quantum computer is that we use superposition and entanglement to do the computation. Okay, there are two types of quantum computer. One is the gate-based, so a little bit like our CMOS logic. We may think in that way. We apply a gate, and you convert a signal to another signal and keep converting and eventually finish the computation. That's the so-called gate-based quantum computer. This is more versatile. And if it is successful, it's going to be transformative to the whole world, right? Like it can speed up a lot of computation exponentially. Another is quantum annealing. Basically, it just use some quantum circuits to mimic the physical circuit and let it just evolve to find the minimum energy. So you can think about this as like hardware simulation. And there are companies doing this already, right? But we are not going to talk about this. And why quantum computer is important? We always heard that, well, it can speed up the computation a lot, right? And nowadays, the bottleneck for many scientific breakthrough is because of the computational bottleneck. For example, we all know that there's a possibility to have a very high capacity battery or come up with some drug can target cancer or target certain disease. But the problem is we need to do a lot of computation to find out the molecule. And to find the right molecule and right reaction require a lot of computation. You either do a lot of experiments, which you cannot complete easily because the combination go up exponentially, right? You just keep putting different molecule, different reagent together and in the hope that you will get a certain molecule with certain property. That grow exponentially is not talking about hundreds or thousands of experiments. It can be billions or trillions of experiments. So you want to do computation, but same for computation. Even for the fastest supercomputer, you also will take millions of years to do all those computation. So if you can use quantum computer to do this, you will achieve the goal much faster. So you will be able to design new drugs, new material, much faster using material engineering. You can also do computation, right? Think about how I can improve the speed of the plane or the rocket through some engineering that need a lot of fluid dynamic computation. They are difficult, right? Quantum computing allow you to have secure communication. So now in principle, every communication can be broken, right? But if you use quantum computer, in principle, you can come up with a secure channel that even someone try to eavesdrop, you will know that. Then you will just stop that and then re-establish the channel, right? And machine learning, AI is very important now, but again, you use a lot of computing power, right? So quantum machine learning is something that you use quantum computer to enhance the machine learning process, okay? So optimization problem, right? If you look at the news last a few weeks or a month back, IBM and HSBC is a bank, a very big bank, Hong Kong and Shanghai bank in UK, right? They came up with a demonstration on improving the financial performance prediction. Why this is important, right? If you heard about investment, what is investment after all? Investment, after all, is that you put your money into a stock or a portfolio of stock, right? And you hope that it will go up, then you will earn a lot of money. But there are lots of combinations, right? You need to calculate which one gives you the highest probability of return. And that is very difficult to compute. And that's why you see many financial companies already have built a team on quantum computing. For example, Wells Fargo, right? You never think about Wells Fargo will do that, but they do have a quantum computing team. And just to understand better what quantum computer is about, when it's ready, they will just jump into it. Because if they can find a good portfolio, maybe 1 second faster than other company, they may earn another billion more than other company, because the trading in New York Stock Exchange is talking about second or tens of second, right? If you can be faster than others, right? So any questions? That is the why quantum computer is so important if it would. So with this, then let's just go to the basic. What a quantum computer? So let's start with the classical computer. Everything is represented as binary numbers, 0 and 1, right, in classical computer. So how do we represent it physically? You can use coin, head and tail, happy and sad, switch, open and close, and that's what we're doing. Transistor, right? In our chip, we use transistor on, off to represent some signal, right? Now, quantum computer is nothing more than that, actually, if we only allow something called basis state, right? So now here, you need to take it for granted because you have not learned it before. You can look at my video, but basically, same, right? Quantum computer also have the so-called basis state or classical state. They also have 0 and 1. So basically, if that is the case, if you only operate on 0 and 1, I can use head and tail to represent it also. Happy and sad and switch and on, right? So the point is that there's no difference between the classical and quantum computer if you only operate on the so-called basis state. But because it's quantum mechanics, quantum mechanics tells us that we actually can have a state in the superposition of the classical state, right? So if you have a register, right, you do your FPGA or whatever, you say, okay, I put 0, 1, 0, and it must be 0, 1, 0 or 0, 0, 0, right? It cannot be something between 0 and 1 and then 0, 1. Right? So because there will be an error, but quantum computer allow us to do that, because when you explore quantum mechanics, instead of just 0 and 1, it can be a linear combination of 0 and 1. So it becomes alpha 0 plus beta 1. Make sense? Maybe not, right? But you need to accept it for now, because we don't have time for linear algebra. So one way to think about it is that instead of head and tail, it's just like spinning a coin on the table. And I don't know whether it's head and tail. I say that it's just a linear combination of that, right? It's almost like you ask, how do I feel today? I won't tell you that I'm happy or sad. I just said 60% happy, 40% sad. This is like kind of superposition in this way, right? Some feeling like that, but of course it's more rigorous. So it is powerful because we allow it to be in a superposition state. So it's a combination of the classical state. Let's look at why this is profound, right? Now, on the left, I show the classical register. How many bits do we have? Have you learned this already? How many bits do we have here? This is a register storing how many bits? 4 bits, right? So you can store 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, 1. Now, I know you have many very diverse background, because some of you might be just freshmen, some of you are senior, so you have taken different classes. So don't worry if you don't understand all of them, right? Just take the main point to get a feeling if you don't have the background. So here I have 4 register. I can store 16, 4-bit register. I can store 16 possible values. So if you go to quantum register, I also only can store 16 possible basis value or classical value. But the main point is that I also can form a superposition of this. So let's go back to here 1 bit. I have 1 bit. Classically, I can store either 0 or 1. Quantum mechanically, I also have 0 or 1 classical bit or basis state. But I also can have alpha 0 plus beta 1. So same here. I have 4 bits, so I have 16 basis states. Then I also can have a superposition of 0 to 15. So it means I can have any state alpha 0 plus beta 1 plus gamma 2 plus delta 3, keep going, right? So if I have n qubits, then I can have 0, 0, 0, all 0, and then 1, and then 0, 0, 0, 1, 0, all the way to 1, 1, 1, 1, right? If you have not counted it before, this has 2 to the power n possible basis state. Now, forget about this if you don't understand, you have not learned about register or binary number. But the point is that what you need to take home is that, well, 1 qubit, I have 2 basis states. 2 qubits, I have 4 basis states because I have 0, 0, 0, 1, 1, 0, 0, 0. 4 qubit, I have 16 basis states. It grew up exponentially, 2 to the power n. Why is such a big deal? If I have 300 qubit, let's say I use electron spin to encode the qubit, it has 300 electrons. How many basis states do I have? It's 2 to the power 300. Now 300 is nothing, right? Everyone can count 300 easily. That's not a lot. But however, it has 2 to the power 300 basis states. It means that in order to describe this state, I need to put the alpha beta, the coefficient of that, I need 2 to the power 300 basis number. 2 to the power 300 compressed coefficient. That means just to describe the state of 300 electron, I will need to store 2 to the power 300 compressed number, which is 10 to the power 90 compressed number. 2 to the power 300 is equals to 10 to the power 90. And that is a lot because the number of atoms in the universe is less than 10 to the power 82. The number of bytes, including those in your iPhone and your laptop, we add them all together, is less than 10 to the power 21. So just to describe the state of 300 electron, you need 2 to the power 300 compressed number, which cannot even be stored in all the storage we have in this world. Any questions? Right? But the point is that it grew up exponentially, right? Just 300 electrons. And that's why it contains a lot of information inside 300 qubit. So if it is like this, so what? Yeah, looks like it has a lot of information. Maybe it is a very powerful storage, right? Isn't that? Because I can store a lot of number just with 300 qubit. But whether you can do it or not, that's another thing. But it can store a lot, right? Another thing is, we need to remember that quantum mechanics is linear. So what does it mean? So if I have a state that is in the superposition of the basis state, like this one side, equal to 0.50 plus 0.51 plus 0.52 plus 0.53, I apply an operation to this state, is equivalent to applying the operation to each of them at the same time. So it means that I can do the parallel computation at the same time. Now this is only 2 qubits, so I have 4 basis states. Remember that if I have 300 qubits, I have a lot, 2 to the power 300 basis state. That means I can just use one computation. I finish the computation of 2 to the power 300 input. at the same time. And that's called quantum parallelism. Okay, so sometimes you can think it as like you have parallel universe. They all operate at the same time. So that is how you speed up the computation with quantum computer. But it's not easy to do that. You need to think of a good way to encode it and also decode it, right? So we talk about superposition. Superposition has profound amount of data. And then because of superposition, we can do parallel computation, right? How about for measurement? Now let's go back to the measure. If I have a spinning coin on the table, how do you know whether it's head or tail? If I say, this is like a superposition of head and tail, what will you do? In reality, it's spinning. You want to find head or tail, what will you do?
Wait for it to fall over.
Wait for it to, very good. So this is a very good analogy, but I'm not that patient. So I'm going to just stop it, right? It's the same. When you stop, what happens? It can collapse to either head or collapse to either tail, right? You all agree? That is the same for quantum mechanical measurement. If you have a state which is a superposition of 0 and 1, and you try to measure it, okay? How you measure it is another thing. You try to measure the state. It turns out that it will collapse to either 0 or 1 randomly, just like what you do to the spinning coin. Okay? And it's so random that you don't know which one will come up. And that's why Einstein said that the God doesn't play dice. He didn't believe in quantum mechanics, Albert Einstein. He thinks that either quantum mechanics is incomplete or wrong. And he tends to think that it's incomplete. Because he cannot accept the fact that if I measure this qubit, whether it comes out to be 0 or 1 is completely random. You think that maybe we're just missing some physics. Maybe there's some hidden variable, what we call hidden variable, that actually you will determine whether it's 0 or 1. But up to now, after so many decades experiment and verification, it doesn't point to that fact. And we have so-called the Bell inequality violation. They got Nobel Prize 2 years ago because of that. Show that indeed this type of randomness cannot be explained by classical statistics. So there is something special about quantum mechanics, right? So for us, we just accept that, yeah, it's random. And it only depends on the size of the coefficient square. This gives us the probability of getting 0 and probability of getting 1. And that's it. The rest is randomness. Okay. Now, I also want to introduce another thing. We talk about superposition, right? You already know that, say, okay, quantum computing or quantum mechanical scale is contain many states at the same time. So it's profound. It has a lot of information. You can be a quantum memory. You store many things at the same time. The size of the memory can be larger than all the memory combined in this world, just for 300 electrons. We also say that you can have you can do parallel computation because of the linear property. But another important thing is entanglement. So what is the meaning of entanglement? I don't want to go to detail, but basically it's like this. This is a 2-qubit state because I have 4 bases, 0, 0, 0, 1, 1, 0, and 1, 1. Okay? Now, if you treat this like multiplication, take it for granted. Just trust me, mathematicians say that this is just like multiplication. I can make it into the multiplication of 2 electrons, right? So this is a 2-electron system or 2-spin system, right? So you see that I can describe this whole state. So this 2 electron has a certain state. And now I say that, I don't need to describe them at the same time. I can just say that, okay, what happened to the first electron and what happened to the second electron, and then I multiply them together. What we call them the tensor product. It's pretty easy. Let's say I have 2 students, they actually don't talk to each other, they don't know each other. Then their what they are going to do tonight may be not related to each other because they don't know each other, right? They won't go hang out together. So I say, okay, this student is doing this student is doing this. It's the same as describing what happened to these two students tonight, right? But what if these two students are very good friends, right? They always study together or play together. So in order to describe them together, I cannot just say what happened to this student that individually and what happened to student B individually. Because what student A is going to do is going to affect student B's the plan by student B, right? For example, let's say student A said, they say, I'm very sad tonight, I want to go out for a drink. And because the other student is his or her good friend, then, oh, you go out for a drink? Okay, I decided not to study. I will go out for a drink with you, right? So they are correlated. So this is like entangled state. There are some states you cannot never factorize into two individual systems and describe them individually, okay? So just remember something called entangled states, and they're very special. It's talking about two systems are correlated to each other. We can look at an example which Einstein called it spooky action. I have two electrons which I prepare on Earth, and I make them into entangled states. Up, up, down, down. Now you see up, up, and down, down is just like 0, 0, 1, 1, right? Whatever inside is just a description. So I try to say that it's a superposition of both spin up and both spin down. A superposition again, right? These are the classical state, right? Because spin up and spin down, you measure them, they're classical, spin up and spin down. But now I'm saying that these two electrons, half of the chance they are spin up, half of chance that they are both spin down. So this is superposition state. Now if I move, I'm very careful. Let's say I'm able to build up a very secure and safe channel. I keep one electron on Earth and then move another electron to another planet or a star 100 light years away, which means take the light to travel 100 years to come here, right? Really, really far. And they are still entangled, right? This is entangled. So they still have this correlation. Now, if on Earth, I try to measure my electron, this electron is really far away, 100 light years away, right? I measure my electron. And because due to what we said earlier, the basic state are up, up, or down, down. So when I measure the electron, I'm just like measuring the system. The system will collapse just like the spinning coil, right? It will collapse to either up, up, or down, down. That's what quantum mechanics tell us, right? So let's say it collapsed to up. And since I only have up, up, and down, down, I don't have up, down, right? Due to this state. Then it means that the other electron, 100 light years away, also collapsed to up. And this is what spooky about is that I measure my electron on the Earth and it collapsed to up. How come the electron 100 light years away knows that my electron collapsed to up already, so that it also collapsed to up? Did you see what happened? Because if I get down, it will also down. No one is measuring this electron, but it becomes up and down. It looks like I can transmit information faster than the speed of light. Because once I measure it, the electron 100 light years away, feel it, and then it also collapses to the same direction, right? But no worry, there's no problem with this because you cannot use this to transmit information faster than the speed of light. This is not really a transfer of information if you go deep, right? But the interesting thing is that this is like something that we don't have in classical, right? But to prove this, right, it goes to actually Heisenberg uncertainty principle and then Bell's inequality, and which eventually lead to the Nobel Prize 2 years earlier. But it's just enough to show that why entanglement is so special. And why we want to find a special thing, because if anything that is not special, we can do it classically. Then we don't need quantum computer. So you will always see that people will say, hey, we use entanglement and we use superposition, So we can solve the problem faster with quantum computer. But you need to be careful. Some algorithm actually can also be solved effectively using classical. So this is something you need to pay attention to. But anyway, if you want to be different from classical computer, you definitely need to use superposition and entanglement. That's it. Otherwise, I can use a classical computer to solve all the problem. Okay? So this one, that's why I say entanglement and superposition are important. So we have been talking about the state of a system, right? State is just like my state. You can describe any state. Like I'm standing, there is a state. There's another aspect. I'm talking. Maybe I'm very excited when I'm talking. Then that is my state, right? Now we say in a quantum system you have states. It basically is just a vector. And then what is a quantum gate? Now this quantum system is actually very boring. It basically is just that a passive system sitting there, and you need to do computation. And so you need to apply quantum gates. What is a quantum gate? So it's different from what you learn in classical circuits. What is a gate? Like inverter is a gate, right? A LAN gate is a gate. But what are they? You actually have an NMOS, PMOS arranged in certain way. You input a logical signal, you get something out. That you see it propagate on the chip from left to right in the space. But a quantum gate is nothing. Usually it's just a laser or microwave pulse. So this qubit is sitting there, it's spin up. I shoot a microwave pulse, I shoot a laser pulse to it, then it start rotate to other locations. And that's why you need to pay attention to this. Sometimes people use something called broad sphere. This can be confusing, but you just take it for granted now. The state of a qubit can map to the surface of the broad sphere. So broad sphere is just like the Earth, right? So basically, a state may be just like, I'm sitting, I'm at San Jose. So a quantum gate is just like I take the flights from San Jose to New York. You need to rotate on the surface of the Earth. So quantum gates is try to rotate it about here, right? So there are different gates. For example, NOT gates, control NOT gates, they have classical counterparts. But more important is there's something called like Hadamard gate, which can create superposition. For example, this H gate applied to the 0 state, it becomes a superposition of 0 and 1. This won't happen classically. Because for classically, either go from 0 to 1 or 1 to 0, or 0 to 0, 1 to 1. You cannot go from 0 to 0 plus 1. You don't have such thing, right? And that is the special case in quantum computing. And this one is a LAN gate. What's so special about LAN gates? I tell you, I have a gate that is a LAN gate and the output is 1. Do you know what's the input? You don't know because 3 pairs of input will give me 1, right? But if I tell you this is a control NOT gate in quantum computer and the output is 1, 0, you will know what is the input because it is reversible. That is special about quantum gate. But that makes sense because it's just physics, Schrödinger equation. Right, and we talk about rotating the state on the broad sphere. So if I can take the flights from San Jose to New York, I can also take the flight from New York back to San Jose. I just reverse the direction of the gate operation. Okay, so quantum gates need to be reversible. So if someone tell you that, or you find out something that's not reversible, you know that is not a quantum gate. Something goes wrong. So we have the input. We go through many gates. Again, what are these? They are just laser pulse and microwave pulse. So you are not saying that I'm going to go through a lot of circuits. Let's say I have 1 trillion gates. It doesn't mean that I need a silicon chip with 1 trillion gates to do the processing. It actually means that you sit there, I shoot 1 trillion microwave pulse to the qubit. And that is the 1 trillion gate. And then eventually you do measurement. Before you do measurement, you can always go back, reverse, if I apply a reverse gate. Okay, so that is another characteristic of quantum gates and circuits. A few more important things is the so-called no pooling theorem. So in classical information theory or computer, you always can copy, right? But actually, you think about yourself, how do you copy? You actually need to read it and then copy. Let's say you copy your homework from your friends. You need to read it, see what your friend did, and then you copy, right? But in quantum computer, can you read something and then copy? When you read something, it means measurement. What will happen when we have a measurement? We just said the state will what? Collapse to 0 or 1. You lose the information. So even you cannot read it and then copy. This is the first thing. And you can prove that it cannot clone. If I say, okay, here I have a qubit, it is under certain states. I don't know what it is. Can you copy to your quantum computer? The answer is no. You cannot copy. Okay? So that is one problem. Now, then how do we do error correction? So in classical channel, let's say I call my mom very far away. I say something. She doesn't hear well. The channel is noisy. I told her that I'm coming back in November. She cannot hear. What will I do? Just keep repeating, right? She said October? No, November. Or December? No, November. I say 100 times November. And maybe she got 51 times November. Then you're coming in November. Because based on the chance that she hear wrong, should not give, there's a low probability she will hear 51 times November, right? So that's so-called repetition code. You send 0 to someone, it's noisy, just send more 0. This whole 0 represents 1 0. Then maybe you get 1 or 2 flip, you use majority vote, right? If you have more 0, then I think you are saying 0. If you have more 1, then I know that you are sending me 1. But in quantum computer, you cannot do that because you just cannot copy. So if you cannot copy, how can you use repetition code? So they use something called syndrome measurement, which we don't go into detail. Basically, this is the qubit I'm going to send. It has a noisy channel. It's going to apply noise to this qubit, right? And then there will be a problem. What we do is that before we go through this noisy channel, we entangle. This is a control NOT gate. I did not go into details, but we entangle this qubit with other ancillary qubit. So basically, we make some correlation between these 3 qubits. And why is important? Because if then one of the qubit got flip, got noise, because they're entangled, the other will feel it. And then at the end, we will measure the ancillary qubit. It's like this. It might not be a good example. Let's say I go home, I see my son is crying, for example, exaggerating. Then I don't need to ask my wife, are you not happy today? Maybe my wife is not happy because just by seeing that my son is crying, then I can expect, he must have pissed off his mom and got scolded, and that's why he's crying, right? Because I know there's an entanglement between my son and my wife. So I don't need to ask my wife because I know if I do the measurement of my wife, I will be in trouble. I just measure my son, right? So I don't disturb the state of my wife. Something like that. And that's called syndrome measurement. And that is what we do for error correction. Okay? So to respect your time, I know we have different background. If you want to go, you feel free to go now. If you still have people stay, then I will go to the hardware part. Okay, I will just try to finish it maybe in another 20 minutes. So for quantum computer, if you want, we are talking about some of the basics, right? But how do we implement it? There are some criteria, 5 essential criteria, if you want to implement a quantum computer. First, you need to be able to implement 2-level system. You probably understand why 2-level now, right? Because we have 0 and 1. And what it is different from classical quantum computer is just that the superposition, it can have superposition of 0 and 1, right? And second thing, you need to be able to initialize it to 0. So don't take it for granted. You might think that, initialize a classical qubit to 0 is easy, just write 0. But for quantum computer using physical system, sometimes it's difficult to initialize it to 0. You don't only use 0 state at the beginning. due to error correction and many algorithms, you need to keep initializing zero. You need to have some zero qubit in order to do the computation. You need to have a long decoherence times because quantum computer is very prone to error, noise, which is understandable, right? Because quantum mechanics only happen in very tiny object, like electron, right? And of course, electron can get disturbed very easily, right? And you need to have a universal set of quantum gates, and basically you need to have some 1 qubit gate, but more importantly, you need to have an entanglement gate, which is understandable again, because without entanglement, you cannot solve any interesting problem, or you cannot solve any problem that classical computer cannot solve effectively, right? And you should be able to do measurement. After all this computation, if you cannot do a high fidelity measurement, again, this is impossible. Actually, many of them are the same for classical computer, but we took that for granted. You never think that I cannot do measurement in classical computer? Why I cannot read out the register, right? So we never think about this. But this is not trivial in quantum computer. So how do I implement a qubit? I always want to try to find out a pedagogical relationship to a classical example to explain the qubit, but I cannot, because everything is classical. I cannot explain it. The only thing I can do is by emotion, actually, right? I really can say that I'm 50% happy and 50% unhappy today, because I can come here to talk, I'm 50% happy, right? And then something else happened, 50% unhappy, right? But these are all hand-waving stuff, right? So what we can do is electron. For electron, if you don't know yet, it has something called spin. Okay, so if you have not heard about that, just treat it as a spinning charge. Although that is not the case, it just is property. Okay, it can have spin up or spin down, depends on the measurement. So when you have spin up and spin down under an external electric field, then you have different energy. So spin up and spin down electron cannot be distinguished if there's no electric field, magnetic field, no external magnetic field, right? So I can say this state is in a superposition of spin up and spin down. Another very interesting thing is photonics. For example, here actually connected to one waveguide, I shoot one photon, only one photon. Photon is what? The elementary particle of light, right? One photon to it. Then where will you go? Of course, it either go up or go down, right? Very simple. I just go to the corridor, to the IEEE office. There are only two ways, either turn left or turn right, right? But they have the same probability. So which one is on top, which one is at bottom? If you don't try to look at me, you don't know where I go, left or right. So I'm in a superposition of these two paths. Until when? Until you measure it, until you take a look. Oh, actually you turn right. Then I won't be on the left, right? So there's something very interesting about quantum mechanics, that even the position of one electron of molecule on my hand has a finite probability to be in next room. Actually, it's not zero, maybe very low probability, right? Another thing is so-called superconducting qubit. A superconducting qubit becomes more demanding now, but basically we form a superconducting island. This is something called Josephson junction. We will touch upon this later. But basically, just feel that this is an island, capacitor and capacitor. And you will learn that if you have two capacitors form an island, what will be between the capacitor? Some isolated electrons, right? So, but we have pair of electrons, which called Cooper pair, but doesn't matter. What I want to say is just say that, how do you encode the information? It's saying that I either have one extra pair of electron or a zero extra pair of electron. And they form a superposition. So it's as weird as here whether I have one more audience or zero more audience. Okay? If I have zero more audience like what we have now, then the state is zero. If someone came in and sit there, then the state is 1. And now I can have a state that is a superposition of with one or not zero more students sitting over there. very weird classically, but quantum mechanically for those microscopic systems, it is valid. Okay. Now, but the point is that their energy level is separation is very small. So you will lose the state very easily to decoherence. So here on the left, on the right, I show a plot. This x-axis is the temperature. Our room temperature is 300 Kelvin. And this is here. And if you remember the thermal energy, it means the equivalent energy of the agitation, right, at room temperature is about 26 millivolt, milli-eV. But the energy separation of a superconducting qubit is very low. It's only 0.02 milli-eV, which is equivalent to about, 0.23 Kelvin, a very low temperature. So because of this, we need to put it in something called dilution refrigerator. Dilution refrigerator cool down your qubit to about 10 millikelvin. What is the lowest temperature that we can achieve theoretically? Do you know? Zero. Yeah, that is the lowest one, right? So 10 millikelvin, just saying that is about 100th Kelvin above the absolute zero. Okay, our temperature is 300 Kelvin. Okay, so it's very low. So that's why we need to put in dilution refrigerator or something called laser cooling for the trapped ion case. But doesn't matter. The point is this: it does have something called decoherence time, which we don't go into details here. But basically, for example, if I'm at state 1, it can go to state 0 eventually. You lose the energy. But more importantly, if I'm in the state of 0 plus 1, it can go to other combination. 0 minus 1, 0 plus I1, 0 minus I1, etc. So now, if I lose the phase, with this means that I lose the phase information because the coefficient in front of it contains the phase information. Then I will lose all my quantum information. So they are very fragile. Okay, so just want you to be aware of that. If you forget anything, remember the number 20 millikelvin. That is usually the common operation temperature for solid state quantum computer, except for photonics, but superconducting and speed. So from here onward, you will see a lot of math, no need to worry, and that's why I can go fast. I just want to relate this to your EE knowledge or your future EE knowledge. First of all, what is this? This is inductor, this is capacitor, and this is a LC tank, right? Resonator, right? Oscillator. So it turned out that if you cool it down to very, very low temperature, it will have a quantization of energy. Or on the other hand, you can say that you can store 0 or 1 unit of photon. Okay, now you may get confused. Why you talk about photon? We are electrical engineering. We have been talking about EM wave. But remember, what is light? Light is also EM wave. It's just at different frequency, right? Everything is electromagnetic wave. Red light, blue light, right? So when we can, that's why the terminology is photon, because they are the smallest unit of, the particle of light, right? So if you don't have any energy, you basically say, oh, you don't have any photon, no light inside. When you go to very low temperature, you can have 0, 1, 2, 3 electromagnetic wave package or photon. Okay, so we can use this to encode the information, 0 state and 1 state. Okay, but however, this one is not good because you have even spacing, which can cause problem. We want something that has uneven spacing, like this. Like I will show later. So this one won't work well. So let's just digress a little bit. You just take it for granted again. In superconductor, what is superconductor? Have you heard about superconductor? What's the characteristic of superconductor? Zero resistance. Yeah, and it always expel magnetic field. There are two things. Yeah, Yes, zero resistance. And it only occurs at very low temperature. So when there is superconductor, electrons will pair up together. They are no longer individual. They become a pair. And we call it the Cooper pairs. Okay? Take this for granted, Cooper pairs. So in a superconductor. And they can describe by something called phase, which we don't want to go into detail either because of time. So that's why someone called Josephson came up with this structure: superconductor, insulator, superconductor. This looks like a capacitor, right? But they are superconductor. And we also don't need to worry about that. The point is that it has inductance. And the inductance is nonlinear. It means the inductance depends on something called phase across this junction. Okay? Because of time, I won't go into that, but the point is, remember, it's nonlinear. And because of this, then this quantization, originally this one, the blue curve, is for the LC tank, you have even separation. But now, if I replace the inductor with the Josephson junction, I have a less parabolic landscape, then I have different separation. Right? Again, no need to worry about this, but the main point is just to tell you that by combining a capacitor with a Josephson junction, we have a well-defined 2-qubit system. That's it. Okay? And I will skip this slide. And then, how do we do 1-qubit gate? Well, as long as you can rotate about the Broad sphere through 2 S's, then you through some Euler construction, you can rotate from any point to any point. First of all, what is a quantum gate again? Is the movement of a state on the Broad sphere, right? Like what I just said, from San Francisco to New York or San Francisco to Toronto. Then they represent 2 different gates. So if I can come up with something that rotates above the North Pole, rotates above this x-axis, then I can go to any point on the Earth. And that is the 1-qubit gate. Now, how do you implement 1-qubit gate? A lot of math, we don't go into detail, but just want to tell you, turn out everything is just electrical engineering. You pick the right capacitor, you generate the right pulse, and after that, you will be able to rotate it on the Broad sphere for the right angle and right direction. Okay? Even more math, no worry. How do you do 2-qubit gates? How do you let them interact? It's also on the left is a transmod, right? LC10 on the right is another transmod. They are coupled by a capacitor. And what you want to do is to change their frequency so that they resonance with each other. Then you will obtain a 2-qubit gate. Again, this is too deep, so I won't go into detail. Right. So then I come back to what I told you earlier. After all, what is a superconducting quantum computer? On the top, you have FPGA, you have Python programming, you have arbitrary waveform generator. You generate the waveform you want. For example, this one. I can use arbitrary waveform generator to generate this. And then it will go through the mixer, go to higher frequency, and then you interact with the qubit. Then it becomes a 1-qubit gate, right? And then you can change it, do the computation. And here just show you the math, but not necessary. You can read my book if you want for the details, but just want to say everything is electrical engineering. Mixer, this is the IQ mixer, what we call the IQ mixer. You will learn in your microwave circuit class. And how do I read out the results? I just want to say one thing is that this is the qubit and this is the resonator. So it turns out the resonator resonance frequency depends on the state of the qubit. It's not difficult to understand, although it's not a good analogy. I just say that I can have 1 or 0 extra student, right? Now, instead of coming to see whether you have 1 or 0 extra student, what you can do is look at the vibration energy of this building. if I have one more student, the vibration frequency will be slower, right? In some sense. So what you are trying to do is you measure the resonant frequency of the resonator, and somehow you will deduce the qubit state. That's called dispersive readout, or also a non-destructive readout, right? Because of time, I'm rushing a little bit. I will skip this one. So I did not spend too much time on hardware because it's also difficult. But basically, the point is that up to now, everything is classical except the qubit, right? So, and I really don't think you lose anything by spending more time on this classical control, because if quantum computing doesn't work, you go back to your old industry. So it open a new dimension for you.